delay, speeding up development of crops so that yield goes down. That's obviously important, and lots of other things. The Great Barrier Reef being one that worries us. But the reason that the effects at the physical scale are generally small is shown in this diagram here. Greenhouse gases create a radiation imbalance. Most of the extra long wave, which is coming in on the left, and this is the globe, this is the ocean, and this is the land. So let's concentrate on the land. Here's the big increase in downward long wave radiation, a small decrease in short wave radiation. Short wave radiation is what we want for photosynthesis. Long wave radiation is sort of waste heat. Where does it go? It mainly goes in a big increase in outward long wave radiation. So basically, garbage in, garbage out. There are small increases, a small decrease in shortwave radiation out, and there are small increases in latent and sensible heat. Latent heat being evaporation, sensible heat being what drives eagles and gliders up into the air. So most of the effect is of temperature itself. And as I said, temperature is important in certain ways, but it's not that important for the dynamics of weather. Now, the funny thing is that although we would expect evaporative demand to be increasing, the best measure we've got around the globe, which is pan-evaporation rate, has surprisingly been decreasing now for more than 40 years. The major reasons for the decline, actually, is that the wind speed has been going down around the globe over land. Not necessarily over the ocean, maybe going up over the ocean, but the wind speed over land has been decreasing. In Australia, it's been going down by 1 centimetre a second per year. Over the last 30 years, 30 centimetres a second, which is 0.3 metres a second, loss of wind speed over that period, has to be seen in the context that the mean wind speed is 2 metres a second. So that's a 15% reduction. And a drop in wind speed has a big impact on all sorts of things to do with farming. The other thing which is contributing to a loss of evaporative demand is what we call global dimming, as opposed to global stilling, which is the reduction in wind speed. Global dimming has been occurring in Asia, associated with the Asian brown cloud, and it also was occurring earlier on in Europe and the eastern United States, but changes in pollution laws have cleaned that up. There's no evidence, in my opinion, but this is I have to say, because Francois urged me to tell when things were controversial. It is controversial about drought, but my conclusion is that there's no evidence for the increase in the frequency or intensity of droughts. There's a paper by Sheffield et al. In Nature that explained that. But of course, droughts will continue to occur, and they'll continue to disrupt agriculture. So climate variability has always been a big problem, and in my opinion, will remain a big problem, the major problem. But we must not confuse climate variability with climate change. And so droughts, in my opinion, are more associated with climate variability than they are with climate change per se. Just some practical data showing the declining wind speeds in Korea. The diagram on the left is the average wind speed on the stations in South Korea. I should point out that the scale goes from 3.4 meters a second down. This is about 2.6. So it is offset from zero. It's not approaching zero. It can't go to zero. And the diagram on the right shows the maximum wind speeds, but they're also going down. So that's 11 meters a second, and that's 7 meters a second. Now, it's important to realize that while it's well recognized now that wind speed is decreasing around the globe, it's not something that's predicted in the general circulation models. So it's not in the climate models that we use to make predictions about the future. These are aspects that are unclear and need more work. There's lots of work needed on the basic physics of climate change. Now, I've put this slide in, which shows the mean annual water balance over the globe, ocean and land. And let's just concentrate on land, because that's where most of the farming occurs. You see that precipitation will go up by, on average, 41 millimeters a year. Evaporation will go up by 20 millimeters a year, and the difference, which is runoff should increase by about 21 millimeters per year. Now that's averaged over the globe, over the land base of the globe, and it's the average of about 39 runs of 20 different general circulation GCMs. But of course, that's an average, and none of us lives in the average. No farmer works in an average place. Everything's got a, these are just aggregates over the all land, so that has to be carefully taken into account. But you can see that if runoff is increasing on average, it's pretty hard to say that on average the world is getting drier. I'll come back to that point. Now, farmers need to know in their location, as we heard in the last presentation, we need granularity. Now, previous research from Held and Soden demonstrated that the wet get wetter and the dry get drier. And this caught the scientific public's attention. More precisely, it was shown that P minus C, precipitation minus evaporation, the change in that was proportional to the pre-existing precipitation minus evaporation. So the increase would be greatest in places that had greatest precip, and that would follow Clausius-Clapeyron scaling, which is a 7% increase per degree centigrade. Now that seems to be true, averaged over latitudinal zones. Much of the subsequent research on impacts has been based on this assumption that the wet will get wetter and the dry will get drier. The question is, though, does it hold locally? Because that result was a latitudinal band average. Let's look just at the lower three graphs, which is land. There's a latitudinal variation of precipitation and evaporation, and I hope you can see it better than I can. There it's plotted versus latitudinal bands, and it's rather noisy when it's restricted to land alone. Whereas you can see that when the ocean, it's a good relationship. Latitudinal bands in the ocean, changes in precipitation minus evaporation are proportional to the pre-existing ones. But it's not true for the land. And when you look at individual points, it's just a shotgun. So there's no a priori reason to think that places that are wetter now will become wetter still and dry places become drier. There's no reason to think that from the models, I emphasize. And we're talking about the models here. These are all results aggregated from models. Nevertheless, there are projections for some areas to become drier, and some of those are important to grain production. Mexico, Central America, Chile, Southern Africa, the Mediterranean, possibly Southern Australia. But once again, these are modeled outcomes, and you've got to take it with a grain of salt. Let's look at the actual observations. What do we see in the actual observations? Well, the observations are But Mexico hasn't gotten drier. Mexico's actually gotten somewhat wetter over the last 70 years. And Northern Australia's got wetter. The trend of the mean is what is shown there, the mean over the 70 years. And it's quite variable. What does it look like when it's aggregated? If we aggregate, we find it's virtually no change in the observed global total precipitation. But of course, once again, that's aggregated over the total land, and nobody lives over the average land. So even though temperature's gone up by about 0.7 of a degree, we can't yet really decipher much increase in rainfall at the global scale. But that's partly a problem of measurement. There are less reliable measurements now in 2017 than there were in 1960. As bureaus of meteorology around the world are passing the work to satellites and to drones, and we've got far fewer actual meteorological stations run by meteorologists than we had 50 years ago. What's happening to the variability of rainfall? This is now, once again, measurements, not theory. This is measurements. So this shows the trend of the temporal variance over that same 70-year period. And the area that I know, the reason for that is that Northern Australia has become much wetter. That's just an example. I'm not sure how experts from Africa and India would relate to their own experience. Anyway, the interesting thing is that, the funny thing is that despite the press that had been given to the Heldon-Soden relationship, in fact, the wet are getting slightly drier, but you wouldn't notice it because a small reduction in rainfall in wet areas has very little impact on humans. But in practice, the interesting thing is that dry sites are actually on average, once again on average, over the 70 years getting slightly wetter. So maybe we need to be careful about what we say about drought for the future. And that raises with me the issue that it's quite commonly thought that increased temperature increases drought, because the two things are correlated. When there's a drought, it's hot. But that's the causality, it's not the other way around. I mean, I'm not saying that increased temperature has no effect on distribution of rainfall, but it's a complicated story. But certainly what we can say very directly is that when it doesn't rain, there's no evaporation. There's no evaporative cooling, there's no latent heat loss, and certainly those dry times become hotter. But the main area of causality is from lack of rain causing lack of evaporation, causing rising temperature. So that's quite different from the increase in temperature caused by greenhouse gases. But anyway, in discussion of drought, and it's important in a place like this where we have people with such diverse backgrounds, there can be confusion depending on the background that you've trained in as far as drought's concerned. So I suggest that we've got roughly 3 different kinds of definitions of drought. One is meteorological, which is lack of rain. One is hydrological, which is lack of soil moisture, and that's often assessed from runoff. And we've already seen that runoff, in the models at least, runoff in the global climate models is increasing. And there's also ecological, which is to do with the reduction in growth and yield. Well, on average, climate change should bring more rain, as we've seen on average, increased runoff on average, and faster growth, partly because of CO2. So on all 3 definitions, there should be less drought in the future, and there should be less drought now than there was, say, 100 years ago. Which brings me to a little bit of biology about the direct effects of CO2 on vegetation. If climate change was as bad for vegetation as we hear, then we would expect that on the global scale, we'd have less primary productivity now than we had in the past. But it's well known that global net photosynthesis is now occurring at a faster rate than has occurred for thousands of years, possibly hundreds of thousands of years. And how do we know that? We know that from the atmospheric record of carbon dioxide, where when the balances are done, much more CO2 is emitted than stays in the atmosphere. Some of it goes into the ocean, but there's about 3 gigatons or more of carbon per year going into the land. The land is a sink on a net scale. That can only be if respiration maybe could have suddenly stopped. We know that's not occurring. What's happened is that around the globe, on average, photosynthesis has increased. The greatest effects are actually in the semi-arid areas because they're the ones where the exchange for CO2 and water are most important. So it's the semi-arid areas where satellite imagery shows a global greening. And it's the effects of carbon dioxide and water use efficiency that are thought to contribute to that. There's a graph from 2012, I think, on the top there showing the increase in, it's actually increasing. It's probably maybe plateauing at present in the present decade, but it's been increasing. And there's good reasons to understand why that's the case. As I said, typically around about 3 gigatons in 2011. Here's a graph of NPP in 2014. These snapshots, though, can be quite misleading because it depends on the year that you take, whether things are green or brown. So we've got to be careful about the nature of snapshots and the extent to which we aggregate. Anyway, the point is that global primary productivity now is greater than it was 100 years ago, and it's probably greater than it was over tens of thousands of years. Now, in the few minutes remaining, I'd like to talk about the biology that I had intended to talk about. Water use efficiency and water use effectiveness. The terms are not the same. Abraham Bloom discussed this at an early Drought, as I did at another conference. If the water use efficiency of carbon gain is defined simply as the ratio of assimilation rate to transpiration rate, then because of the relationship between assimilation and conductance and transpiration and conductance, the shapes of those curves, it emerges that water use efficiency is greatest when the stomata become more and more closed. And in the limit, the greatest water use efficiency occurs, unfortunately, with zero photosynthesis and therefore no growth. So to just go for water use efficiency by itself is not a very useful task. Working with Ian Cowan in the 70s, we defined optimality as the greatest carbon gain for a given total amount of water transpired, which is the least water. It's the same mathematically as the least water loss for a given carbon gain. I'll try and show that on a diagram here. On this diagram, we have the relative response of his E is evaporation rate, transpiration, plotted against conductance. And here is assimilation rate. They've both got curved relationships, but in this particular example, the curvature in the assimilation rate response is greater, which means that when you divide one by the other, when you divide assimilation rate by transpiration rate, it's one of decline with increasing conductance. So if you call that water use efficiency, the greatest water use efficiency occurs when the stomata are closed and when you have no photosynthesis. So that's not a very good way of thinking for the future. But if you think of the CO2 assimilation rate minus some costing of water, and for us it's this Lagrange multiplier lambda, so photosynthesis minus transpiration divided by lambda does have an optimum, in this case here, And it depends on what the value of this Lagrange multiplier is. If lambda were very small, then it would push the curves to have an optimum up here. If lambda is very large, sorry, the other way around. If lambda were very large, it would look more like this. So it depends on the cost of the carbon cost of water capture or the water cost of carbon gain. And it can be thought about in the following way. How should the plant arrange its expenditure of water over a period of a day in order to achieve the maximum assimilation of CO2? It would seem best to avoid those parts of the day which are hottest, where the VPD is greatest. But it turns out, of course, that that's also the time when light intensity is greatest and when you get most photosynthesis. So there's got to be some compromise here. The optimal solution is to shift around the pattern of expenditure of water over a day until you can get no more carbon by any small change. So at this optimum trajectory, the effect of increasing expenditure, which is change in evaporation rate, at one point of time, which requires a minus delta E some other time to balance out, always gives the same increase in assimilation rate. That increase is delta E, where that's the change in evaporation rate, divided by lambda, this costing function, this Lagrange multiplier. So the lesson in a sort of an economic sense is always buy more carbon. If you're a plant, you should always buy more carbon if the price is less than lambda moles of water per mole of carbon. Same argument holds for spatial variation throughout the canopy. If the return on expending a marginal increase in transpiration is dE over lambda at one part of the leaf or one part of the canopy, then it should be the same for the rest of the leaf and for the rest of the canopy. So once again, always buy more carbon if the price is less than lambda mole of water per mole of carbon. So lambda is the ratio of the slopes, the sensitivities of ratio of the sensitivity of assimilation to conductance and the sensitivity of transpiration to conductance. So at a different time of day, you need to have a different stomatal opening to maintain the same ratio of sensitivities. Well, how well do plants follow this economic ideal? They open in the light, they close in the dark, they close with increasing leaf-to-air vapor pressure deficit, but they do not open in general if CO2 increases. Well, that would be a smart thing for plants to do. If the atmospheric CO2 were to fluctuate, it would make sense if plants would actually track them, but of course there's been no evolutionary pressure to do so, and so I don't think it's a great sin on the behalf of evolution.
Sorry, Graham, to interrupt. 2 minutes.
Thank you.
Sorry.
So leaves with large photosynthetic capacity have large stomatal conductance. So that's also a prediction. Now, what about periods longer than a day? If the plants knew exactly when rain was coming, they should just arrange to run out of water at that time, but they don't. But they can adapt to a particular environment, soil water holding capacity, and statistics of rainfall. There's been some work done on this, started by Ian Cowan in '86, most recently by Lou et al. In 2016, and we've got some unpublished work on this topic. The answer is that in an environment with frequent rain and deep soil, you should have a large value of lambda and a low transpiration efficiency. But with infrequent rain and thin soil, effectiveness means having a small DDA, low DI, and high transpiration efficiency. So how do you recognize these genotypes? You can tell from the title that I wrote in the abstract that I suggest doing it by carbon isotopes, but of course there's many other stomatal-related traits and ways of doing it, leaf temperature, canopy temperature, and so on. I'd like to finish on one point that There's been a lot of work done recently on within canopies plotting transpiration rate versus VPD. And I realized by looking at some of their papers, there's confusion about what VPD actually means. So here's my modification of the Pemberton-Monteith combination equation. And this is evaporation rate. This is vapor pressure deficit, D here, but it's only one portion of the whole leak-to-air vapor pressure difference here. So when we use the term VPD, we've got to be careful what we mean. Do we mean vapor pressure deficit of the air, which is a measure of how much more water the air could hold, or do we mean the leak-to-air vapor pressure difference? I'd like to thank Rajiv and Francois and colleagues for having me here. Thank you.
Thank you very much, Graham, and sorry about the rush, but we need to keep on time. We need to do our job.
Do your job.
Okay.